In this video, we're going to look at chemical formulae, some different types of chemical formulae and how we might interpret them and put them together. You should already know that ionic compounds are made up of a giant lattice structure where the oppositely charged ions are all attracting each other in a 3D arrangement. So that means that there's no absolute number of ions. We can't put a number on the total number of each ion that's present in a lattice because it depends basically how big the crystal is. That's why we call it a giant structure. So instead, when we write the formula of an ionic compound like NaCl or MgCl2 or AlCl3, what we're showing there is something called the unit cell. It's the simplest ratio of the elements that are present in that lattice. So, for example, in sodium chloride, the simplest ratio is 1 sodium ion to 1 chloride ion. For magnesium chloride, it's 1 magnesium ion for every 2 chloride ions. And then AlCl3 obviously means 3 chloride ions for every aluminium ion. This simplest ratio you may have heard referred to before as the empirical formula. So we can construct ionic formula by determining how many of each ion are needed to get a net charge of 0, because obviously a compound like a crystal, it doesn't have an overall charge. And this is a really important skill to get on top of quite early in A-level chemistry if you're not already confident, because if you get it wrong, you'll get lots of difficulties in your calculations and also in your balanced equations. So here's some examples of some positive ions from group 1, group 2 and group 3, some negative ions from group 7, group 6 and group 5. If you can't remember related to atomic structure why elements from different groups form these charges, then you should go back and revise that from GCSE because it's quite key information that we'll need when you go back to bonding. So it's just a bit of simple maths. If you wanted to write a formula for a group 1 compound, then if group 1 goes with one of the group 7 ions, chloride, bromide or fluoride, then we're just going to need a 1-to-1 ratio because +1 - 1 equals 0. If we are going for a group 1 with a group 6, then we're going to need to multiply the group 1 by 2 to get 2 lots of +1 and 1 lot of -2. And then if we want to go with a group 1 and a group 5, which is pretty rare, then we've got 3 lots of our +1 ion and a -3 to give us 0. Similarly, we can look at example formulae for group 2. You can see the maths isn't much harder. We've got a +2 and a -2 lots of -1 to give us 0 for our calcium chloride. If we have a +2 and a -2, we just need one of each. And then the only time it gets a tiny bit more challenging is when you've got a combination of a +2 and a -3. So this time we're doing a bit of cross multiplication. Following on, group 3, you can see the trends and the maths that are happening there. So if you've learned to construct formulae before using something called the crossover method, where you take the charges at the top of the ion and then you swap them round with each other, that's fine, it still works, but you should be aware of why the method works, otherwise you're going to come unstuck when the questions get a little bit harder. The reason it works is because, for example, if we look at my aluminium oxide example, that 2 lots of +3 is going to cancel out 3 lots of -2. So just be aware why you're doing the crossover, don't just rote learn things. All of those previous examples were ions that are easily predictable from the periodic table. Group 2 makes a +2, group 7 makes a -1. So you should also be familiar with these things called compound ions, which are shown in the table here. So if you made a bit of a half-hearted attempt to learn these before, then you need to get much more familiar with them now. They need to really be second nature to you. So the ions contain more than one atom, OH, SO4, NO3, etc. This means you can't use the group number to predict the charge. But as you do a little bit more about bonding, you'll learn a bit more about how the electrons are arranged. But one way to think about these ions is that they don't actually form from a single atom losing or gaining electrons. They form when a neutral molecule containing covalent bonds loses or gains a hydrogen ion. So you should know that hydrogen ions have a charge of +1, H+. They're present in acids. So every hydrogen ion that's lost leaves the ion that's left behind with a charge of -1. You've seen that in acid-base reactions. So we can look at the next part of the table and we can see where the ions came from. OH- comes from water losing one single hydrogen ion, H+. SO4 2-, the sulfate ion, comes from sulfuric acid, and sulfuric acid loses both hydrogen ions when it reacts. It has two of them. Nitrate ion comes from nitric acid. Carbonate ion comes from carbonic acid. And the final one, so all of those are negative ions that are formed from molecules losing H+. The final ion has a positive charge, and the word ammonium tells us it's positive. It's made that way to sound like a metal like lithium or potassium, which also have +1 charges. And ammonium comes when the molecule ammonia, NH3, gains H+, because ammonia is a base, so when it reacts with acid, it attracts the hydrogen ion towards it. Any of these ions, not worrying too much about how they forms, you can of course construct a formula based on cancelling out the charges. So if I was, for example, to want a formula for aluminium sulfate, aluminium has a 3+, sulfate has a 2-. The only difference here is that I will need to use brackets if I have more than one compound ion, because I need to take the whole ion and say that, for example, in this case, there are 3 sulfate ions to every 2 aluminium ions. Alternatively, ammonium carbonate, we've got a +1 on ammonium, a -2 on carbonate. So I'm going to need 2 ammoniums for every 1 carbonate and brackets around the ammonium ion. Transition metals form ions with variable charges. This is something we should have learned before. And transition metal compounds usually refer to the charge on the ion using Roman numerals. For example, here iron 3 oxide or iron 2 chloride. So there are a couple of things to appreciate when you're working out the formula of a transition metal compound. The first is that the number always refers to a positive charge. Transition metals are still metals, and metals always form positive ions without exception. But the number doesn't always refer to the numbers present in the formula. So we can use the same ideas to work out the formula of a compound. If we know that Fe has a 3+ charge, oxygen, because of its group, has a -2, we can work out the formula. And in these two cases, it does work out that the iron 3+ results in 3 oxide ions and the iron 2 chloride results in 2 chloride ions. But don't get too complacent about that, because of course you could have something here like copper 2 oxide has the formula CuO and copper 1 oxide has the formula Cu2O. So we're working that out from the charge on the copper. Oxygen remains fixed at a charge of -2. That's a really easy way to get caught out, say, in a multiple choice question. Transition metals can also form negative ions by bonding with oxygen. So, for example, like sulfur can bond with oxygen to make a sulfate ion. Transition metals can also do this. You're going to learn more about these later in the course, but for now, the best thing to realise is that you can work out the charge on an ion you don't know from the formula of the compound, so long as you know one of the charges. So here, for example, nickel carbonate, I have the formula, but I don't know necessarily the charge on the nickel, but I can work it out because I know the carbonate ion has a -2. It's a 1-to-1 ratio of nickel to carbonate, so nickel must be 2+. Similarly, potassium manganate. So I know that potassium has a +1 charge because it's in group 1, and so therefore the manganate ion, the whole ion, must have an overall charge of -1. In this compound, Na2Cr2O7, sodium dichromate, then I know that the charge on sodium is +1, and there are 2 of them. So that means that that whole other section of the compound, the Cr2O7 2-, has a -2 charge. And this means that I can use the formula of this compound to predict what the formula of another compound would be. For example, calcium dichromate would be CaCr2O7. Looking briefly at covalent compounds. Covalent compounds exist as molecules, so they're covalently bonded together. And that means that we usually express the formula as the actual number of each type of atom present, and we call that the molecular formula. Just be careful, we shouldn't be using the word molecular formula for ionic compounds, but this often happens even in textbooks and websites and things because people are a bit lazy. So, most of the covalent compounds you're going to come across will be in organic chemistry where we contain carbon. So you should already know a little bit, for example, about the formulae of alkanes and alkenes. So from this you can see that obviously covalent formulae are different to ionic formulae. So the empirical formula for a covalent compound is not always the same as the molecular formula. You can tell that, for example, the alkanes, if we contain an odd number of carbons, so C3H8, C5H12, they can't be simplified any further because they have an odd number of carbons, an even number of hydrogens, and they never divide into each other, so there's no way of simplifying those anymore. But for alkenes actually all have the same empirical formulae. So it really does depend on how the atoms are joined together. It also means that, of course, we can't just say, unlike, for example, magnesium and chlorine, we can't predict what the formula is just from the fact that something contains carbon and hydrogen, or carbon, hydrogen and oxygen. So most organic compounds are going to contain some variation of carbon, hydrogen, oxygen or nitrogen. And that's why we have our own system of naming compounds like methane, ethane, propane, etc. But of course we can make predictions from general formulae, and if we know the name of a compound, then we know how many carbons it contains and we know more information about it. And then for some molecules, we have, of course, the minute that our organic compounds get a little bit more complicated, and you can see that this is not a very complicated formula, it's only got 3 carbons in it. Even if we have a molecular formula, without any more information, we can't really tell what that compound is, because the way that molecules work is that, particularly for carbon, which can make 4 bonds, there are lots of alternate isomers which have the same formula. This isn't even all the options with the molecular formula C3H6O2. I can think of at least 2 or 3 more, but you can see that this is why with organic compounds you have to use structural formulae, so the CH3CH2 as an absolute minimum, to give us the order in which the atoms are arranged and telling us where the hydrogens are attached, where the oxygens are attached and how. And then displayed formula gives us even more information so that we can clearly see where the double and single bonds are. So don't worry if these compounds are not familiar to you, because you're going to go through a lot more organic chemistry as we go through the course.